Okay, so we are already here at the setup. You cannot see me because somebody has to be holding the camera. But what you're looking at right now, it's basically the excitation part of our home-built confocal setup. As you will see, it looks quite different to the commercial setups that you will see also throughout these demos, so like the Fluorescence or the Leica. Each one of these lines, it's a different laser line that shines one different laser color. Okay, so we have this one, it's a 405 laser line, 440. We also have a 640 nanometer laser line here, 488, and then this one here, it's a 510. And this one here, it's actually, this one here, it's coming from an optical fiber. It's a 560 line. Actually, how it looks, how this all looks from above, and it's a bit the scheme that you can on the reflection. So what we usually do to combine these manually is that we have, imagine for example this 640 line that I have here. This line comes over here, it's reflected by this mirror to this mirror, and then it goes through these three dichroic mirrors. What these three dichroic mirrors do is that they let go through the longer wavelengths and they reflect the shorter wavelengths. So basically what happens is that 640 is the longest wavelength in the whole beam path, goes straight from here all the way there. Okay, so what I've done is that I've turned on all the lasers. It's a bit difficult to see now because if there's light for the camera, there's no light for the lasers. There's too much light for the lasers. But I'll explain you and then I'll turn off the light and then you can see it. Okay? So as I was saying, we have the red laser. You can maybe see it a bit there on my finger. It's reflected in this mirror. You can see that it goes over here by this mirror. And then it goes through all these different mirrors. Okay, this one, and even this one, until here. If we take another beam, like for example the 488 that we have here, then you can maybe see, oh sorry, this is the 510, this is the 488. You can see there the blue laser, it's reflected by this first mirror. Let's see if you can see that. Yes, over there in my hand. And then it's reflected again by this mirror over here. You see that the blue beam, it's there, and then it's here in the palm of my hand. So this one reflects it, and also this one here reflects it, because you can see, if I block the red laser, you can see over here that I have blue laser reflected by this one. With the red laser, it's a bit difficult to see because it outshines the blue laser. And then they're both transmitted through the last dichroic mirror. So here you can see that we have the blue. This is how you combine different laser lines and different excitation lines in a home-built setup. Okay, so how does this work? So as you can see, all the different laser lines are combined into one single point, that it's this optical fiber over there. Okay, this is a optical fiber coupler. This is the actual optical fiber. Okay, it runs all the way through here, and then it arrives at this other end. So all the light from the optical, from the lasers, it's coupled onto this point. Emission comes through here and it's reflected by this mirror and sent onto this cube here. What this cube has is the emission dichroic. So it's basically the dichroic that separates emission from excitation. Excitation is sent again to this mirror and finally reflected to this mirror and gets into the microscope body through this thing that is a galvanometric mirror. That is basically the scanner that is used to move the beam, as I explained for rigs. So this is for the excitation part. What happens at the emission? So for the emission, when the light from the objective is collected, it travels back this path, so it's reflected here, here, and here. But this time, when it gets to this point, it's transmitted, and it gets to the emission part that I'll go with right now. And this is the emission part. So basically, what you see over here, it's Here's where the light is coming from. It's transmitted through here. There's two blends here that focuses it. Then there's the pinhole over here, and a second lens that collimates this beam again, so it focuses to infinity. After this first segment, we start with one first dichroic mirror that splits everything that has a wavelength over 560 nanometer, it's transmitted, and everything below 560 gets reflected. The reflected part gets to this second beam splitter that then is sent onto either one of these two detectors. We have this detector here, that it's a hybrid PMT, and this detector here, that it's a tau spot. What was transmitted through this dichroic, in other words, everything with wavelength longer than 560 gets to this second dichroic, and it's again separated into far red detection over here and orange, or let's say short red detection over here. So this is the whole detection path. As you can see here, we have this black curtain that it's usually covering the full setup because these detectors are very light sensitive. Basically, they're thought to, or they're meant to detect single photons, okay? That's the single photon counting part from the TC-SPC, okay? So this is the whole emission detection part of our home-built setup that, as you can see, it also looks quite more messy than the commercial setups. So welcome everybody to the experimental part of the demo. I'm afraid for this part I cannot show you myself because, as I mentioned, the detectors are very sensitive to light, and then if we turn them on for the camera, you cannot image myself. So what we have here is the program that we use for acquiring data in the FLIM setup. Here you can see the different channels that we work with, laser settings and all the timing. And at the moment, what I have put in the microscope, it's a mixture of two dyes, but the lasers are not turned on. So as you see, we have no signal, okay? You can see here on top, this is the count per seconds that the detector is measuring, so you see that's very low. If I turn on the lasers, you can see now that I have several peaks. So first, let me show you, let's do one by one. I'll turn off the second laser and just have the blue laser, this 485. And then you can see that I have just one peak of the two detectors. Each color line is the detector. Blue is detector number 4, that is what we're using for orange, and green is the detector number 1, that's what we're using for green. And you see that I have just one laser, one pulse, and then the emission is on to the two detectors. If I now turn on the second laser, now you see that I have what I had before, so this first peak here that corresponds to the first laser sign, but now I have also another thing, and it's in this second part, there's a second pulse laser that is the 560 laser that excites this dye, that it's Alexa 546, and we detect it in the second detector. So as you can see, we can separate the green emission that happens before after blue excitation from the red emission that happens after, okay? So this is a very easy way to separate it. This is about TC-SPC. If we go to do FCS, here right now I'm going to show you just one channel. I will show you channel by channel, so apply. This is the autocorrelation curve of my green dye. So you can see that it decays as I explained. Here's the autocorrelation value. And the concentration is appropriate, so I can get this curve. If I now change from 1 to 4, so the other channel, and then I apply, we get the autocorrelation curve of the other dye, that it's a bit more concentrated, and you see that now the autocorrelation curve gets to a lower value. And if I include the two channels, so channel 1 and channel 4, and then apply, what I get is three things. I get the red curve that corresponds to channel 1, so the blue dye, a yellow one that corresponds to the channel 4, so the second dye, and the last curve that it's over here, that is the green one, that corresponds to the cross correlation, that in this case it's very close to 0, because it's not 0 completely, because as you can see in the TC-SPC channel, we have some crosstalk of the blue into the green, of the green into the far red channel, and also emission of the green dye into the red channel, and vice versa. So this makes it until we don't define specifically these window channels. The cross correlation is not 0, but it's very close to 0. So this is what I wanted to show you with 2 dyes. Now about the concentration, let me stop this and change sample. Okay. So because for this next sample I don't need the 560 laser, I will use just the other laser, and I'll actually turn off the other detector. And let me show you. So this is a sample that it's a bit more concentrated. Okay, and then you see that if I do this now, the FCS curve, it's lower, okay? We don't get the maximum, actually, wait, let me put these properly. Let's just get one channel off, apply, and we're getting one channel. So you see, autocorrelation curve doesn't look that good anymore, okay? But now, if I dilute the sample, which is what I'm doing now, you will see that the curve starts becoming higher, and it has more the shape than it has until we reach these points. So this is the effect of the concentration in the autocorrelation curve, okay? You can see how when we dilute the sample, the autocorrelation value increased. So basically that's all for the FCS and the part of the experimental FCS and the TCSPC. Okay, good. Okay, so what you can see here is that we have already loaded a file with 2 dyes. So we have here the green channel, and here is what corresponds to the red channel. So as you can see, and we were explaining before, in the green channel we can see only the peak of the green dye when the green laser pulses. That then shows some crosstalk to the red channel. Take into account also that these units are an exponential, logarithmic, sorry. So this is only like, I don't know, 2000, while here we're going over 10,000 counts per second. That's the data we're collecting. And then when the second laser pulses, we get this second peak of dye here, that it's the and in this case it's a combination of ATO488 and Alexa 647. So how we would do this selection of the different bands that I was talking about in the whiteboard is if I come to this RFP crosstalk channel, that's the one that we would use to image these. Here I can tell the system from where to where I want this to go. This is going to be something like this. Actually something maybe more like this. And now you can clearly see that in the green we're getting just the photons corresponding to the green dye. We have no crosstalk from the far red, that it's Alexa 647, this is Alexa 488. And in the red channel we managed to get rid of this part of green emission and only get this part of red emission. You can see here the intensity trace of each channel. So how does the fluorescence intensity change over time? Here you can see that there's, so these is spikes and everything. So this is what I meant, that the signal fluctuates enough to detect these FCS, but not too much to not allow for to be too much noise. As I was saying, this you can see here the parts of the waves of the decays, but now for the correlation part, as you will see here, if I now correlate here you can see actually it will be easier this way. Here you see that I'm correlating one channel with itself, and here the other channel with itself, and this will be the cross correlation. So if I now correlate these 2 channels, you will see that first we got the, it's calculating it now, we get the green correlation, we get the cross correlation that, as you can see now, because we've removed the crosstalk and we're looking at this channel and this other channel and we don't have any cross correlation, if I now go to FCS Fit, which is the program that we use for this analysis, I'll be able to open these two files that are, well, actually these three files. And then you see that I get here let me make this big, that we have here the three different files, so three different curves. So we have the blue one from the Alexa 488. No, sorry, the blue one is from the Alexa 647, green one for Alexa 488, and the red one is the cross correlation. We can correlate each of them separately, or we can analyze each of them separately. So this one, for example, it's the diffusion coefficient. It's the one for Alexa 647, which diffusion coefficient is something like 310. And then these will give me the diffusion. So here you see I can put the diffusion coefficient here, I can foil it, and then these are the focal parameter aspects. So the actual radius of the PSF and the size. So it's Y dimension. If I now fit this, it goes okay. It will give me, wait, because it did something a bit wrong. I need to tell it to do it again. 0.2. I'll make this one inactive for a second. Start fit. And then plotting settings. Normalization fit in 3D. Wait, I'm gonna actually just record the one corresponding to the FLIM. So as I was saying, if I load just not the crosstalk, but the two, so GFP, VFP, and then RFP instead of so these two, these and these two. And then adjust these and fix it. Now, so here you can see that I can get the focal parameters for each of the two diffusion molecules. You can see that the diffusion parameters are dependent on the wavelength, because then for blue we're using a shorter wavelength for 88 for excitation, and then the focal parameters are smaller than the ones that we have for the red that are a bit bigger. Yeah, so basically with that, we're finished. Last thing, no, I think that's it. So thanks for your attention, and if you have any question, let me know.